Hello everyone, we are going to start the third and final module of this week, where we are going to look a little bit more into stability using simulation and using a very non-mathematical way of thinking about stability. So, one of the things that we've been slowly building up to over the last 2 hours is this plot here, which show that there is an isocline for the prey and an isocline for the predator, and they cross at some point in the middle of the plane, and that is an equilibrium point, meaning that when the system is here, it is going to stop changing. One thing that we sort of glossed over while we were getting to this result is the fact that there are actually more than one equilibrium, and the number of equilibrium that we have is something that should be investigated a little bit more. The definition of an equilibrium is a combination of value of the variables such that all of the derivatives in the system become zero. So one other equilibrium that we have is quite obviously the point 0, 0. And we can see that from the model itself. In fact, we are multiplying it's the population size of the prey times something, population size of the predator times something. So it's fairly obvious that whenever one of these population size is set to 0, there is a chance that there's going to be an equilibrium here. When both of them are set to 0, all of the terms here vanish, and so the system is at an equilibrium. So we have one equilibrium here, 0, 0. Let's annotate that. So it's going to be scatter 0, 0. We're going to have a black point here, and no label. Okay, let me just use a slightly larger size, 8. Okay, so one equilibrium is here. That is the 0, 0 point. Not going to go through how we get to this result, but there is another equilibrium, which is the predator is not here. When the predator is not here, all of the predation terms are vanishing. We are left with a system that is essentially the prey only, and the prey, when it's alone, grows according to the logistic model, so it reaches its carrying capacity, which is 1, 0. So we have one equilibrium, two equilibrium. We have a third equilibrium, which is where the two isoclines are crossing. One thing that we do not have, and that's where something we can show when we look at the mathematics of identifying equilibrium, is the prey is absent, but the predator is here. So even though it is crossing an axis here, there is not an other isocline along this axis, and so it's not an equilibrium. The thing that we would need to figure out is the value of this intersection here, the third equilibrium. So we have the trivial equilibrium, which is no species at all. We have the second trivial equilibrium, which is no predator, only preys. That's a logistic growth. And with the third equilibrium, which is two species are here at the same time, there is a coexistence between the prey and the predator. So to figure out when this equilibrium happens, it's actually not that difficult, because we know that it is a point where this line and this line intersect. And we have an equation for that. So we have delta divided by gamma is equal to, and we have the value of x here, which is r over beta times 1 minus x. So we could transform that a little bit. Let me just put parentheses, because it's going to make our lives easier. We have that. And we are going to divide both sides by this thing. So that is beta over r equal 1 minus x. What is the easy solution to do that? We have, sorry, let me reorganize this thing. We have 1 minus x equal delta times beta over gamma times r. So that's our first thing. That's minus x plus 1. So we do minus x equal this thing's minus 1. And this is finally x equal 1 minus this thing. Okay, cool. So we know that the value at which the x value of this equilibrium is going to be, let's actually run that. It's 1.0 minus p delta times p dot beta divided by p dot gamma times p dot r. 0.6, that doesn't look right. I've made a mistake somewhere. Let me check. I'll make a mistake. So we divide by this. Yeah, so it's delta times beta divided by gamma over r equal 1 minus x. We'll remove 1 from both sides. That's 1, that's minus x minus 1, so x is 1 minus, that should be it. Anyway, never mind, we'll do that on pen and paper. So what we'll do instead is just, we'll just solve the system and use an approximation for that. So we'll solve the audio problem using Perturbation. Using u0, let's do 0.1, 0.1. T-span, we have that, and then p. So let's run this thing, and let's take the last one. Yeah, oh, sorry, the one for the predator, doesn't matter. So let's take the last one, and let's run that for a little bit longer. It's 0 to 1000. Okay, so it's 0.4 and 0.6. Let's do that x star, y star, star. And so that is going to be our final equilibrium, which is x star and y star. Okay, so we have 3 points where the system should not be changing. That is important information because it means that we need to evaluate the stability of the system at 3 different points. That's a point that that's going to become very obvious when we look at the mathematics of stability analysis, but for every equilibrium, we need to ask the question, is it stable? We have 3 equilibrium, so we need to ask the question, is it stable, twice. Let me just use the correct values here. Yeah. So we don't need that. Okay. So the point of stability, it's another way of asking the question, if we are at an equilibrium, precisely on the equilibrium, and there is a small perturbation, is a small perturbation going to grow or shrink? So we take the system and we re-express that as the derivative of the perturbation over time, and we want to know if it is positive or if it is negative. If it's positive, the system is going to move away from the equilibrium, and the equilibrium is unstable. If it's negative, it's going to come back, and then the system is stable. That's sort of the very short version of it. When you will read through Otto and Day chapter on linear stability, local stability analysis, you will see that it's about 50 pages. With a lot more equation than what I just described. But the point is, we want to know if there is a perturbation, do we leave the equilibrium or do we come back to it? Interestingly, that is a problem that lends itself to simulation fairly well. So what we know is that we can set initial condition that are the equilibrium plus or minus some very small epsilon value. Epsilon is what we usually use as a symbol for a perturbation, a very small amount of something that we add to the equilibrium. And then we look at the change of the system over time. So let's say we are going to zoom on, we'll do the first equilibrium. What if there is no prey and no predator and the system is empty? So we're going to do that and going to do xlim equals 0.00.01 and ylim equals 0.01. So this is a very small space that we're looking at, right? The entire plan that we used to look at was 0 from 2 and 0 to 2. Now we're looking at 0 from 100th. So the point is that the perturbation that we need to apply are going to be much smaller than that. They're going to be very, very small, like 10 to the minus 6. When we do the analysis, they're going to be essentially 0, but not quite. It turns out that essentially 0, but not quite is a concept that computers may have some difficulty with. And so we're not going to be using essentially 0, but not quite. We're just going to say, give me something from a random distribution that is close to 0, but at a very, very small standard deviation. So to do that, we are going to add a little package, which is not little. Actually, it's a package, it's regular size, called distributions. Just because I want to show you that the distribution package, it exists. We're going to get back to it in 6 weeks, 5 weeks, I think. Just keep that in your mind. It's what you use to look at statistical distribution and take random deviates from them. We're going to make sure that we update the beginning of a file with using distributions. We're going to install, pre-compile, and so on and so forth. It's good. Let's use that. Okay, so we have our zoomed in on the equilibrium. We have the point where the equilibrium is. What we need to do is say, well, if we apply very, very small perturbations to that, is it going to change the dynamic of the system? So do we see trajectories that goes this way, like in this direction, and are just going to escape? Or do we see trajectories that are sort of like going back to it? So we'll do essentially the same thing that we've done before, which is to say we are going to have a little look at different at different simulations. So we know the equilibrium is 0 here, and we will do a quick. I don't like this epsilon. I like this epsilon. We'll do epsilon x and epsilon. Sorry, it's var epsilon. And epsilon y, they're going to be 2 random numbers that we take from a normal distribution. So the distribution that we're going to use for this example is, it's going to be a normal distribution. It's going to have mean of 0. It's going to have a standard deviation of 10 to the minus 5, I don't know. And we are going to make sure, because it is, we are looking at the 0, 0 equilibrium, and it doesn't really make sense to have negative values. We want to make sure that it's truncated. So it can be like from 0 to 1, right? We're never going to apply a perturbation that is 1 because the standard deviation is so small, but we know that it's at least going to be positive. In fact, we could specify that there is a minimum perturbation that we want to apply, and the minimal perturbation is going to be 10 to the minus 6, I'll say. That is a distribution. We call that the epsilon. I want the other epsilon. This one is better. Okay. So to get the value, the displacement on x and the displacement of y, we are going to draw value from the epsilon, and we are going to draw two values. So for this first simulation that we're doing, we are going to move x 4 times 10 to the minus 6, 4 to the minus 6 steps to the right, and y 1 to the minus 5 steps to the upwards. So I'll do the simulation, and it's going to be 0 plus var epsilon x and 0, 0 plus var epsilon y. And we're going to call that trajectory. So let's have a look. If we want to have a look at that, we call the plot function and call trajectory 1 and trajectory 2. And no label alpha equal 0.1. And c equal TL. Why not? That may be a little bit too transparent. Oh, I see what's going on. Okay. No, so our perturbation is here. It's moving away from the equilibrium, or so it seems. So let's try to see what happens if we use a lot of different random variables here. So we could do for I in 1 to, we'll do like 400. We're going to take the random value here, and we are going to do the same thing, which is add them to the plot. I think the command is display to look at the plot. You know what, let me just do this thing, PL, and we are going to add the things to PL here and show PL. Okay, so what we see here is that we do have some of the trajectories that are moving away. In fact, most of them, all of them are moving away from the equilibrium. If we wanted to zoom a little bit, let's say we do x-axis, it goes from 0 to minus 4, and y-axis does the same. We can see that all of these initial points here, they are going to be moving away from the equilibrium, moving away to the right. And so what that means essentially is that no matter what the disturbance we apply here, we are going to leave this equilibrium, which is a fairly important result. It means that if we have a population that is at the 0, 0 equilibrium, and something changes that causes this population to not be at the 0, 0 equilibrium anymore, it is going to go somewhere else. If we want to go where it's going, we could just zoom out. And it is going to go fairly consistently to this other thing, which is this other equilibrium that we identified. So that's an interesting result that tells us something about the stability of this first equilibrium, and that is to say this equilibrium is not stable. If we add population to it, even by a very small amount, it is going to move away from that. There is a special case, and the special case is that we only add a predator. So we don't add a prey, we only add one predator. So that is going to lead us to coming back to the equilibrium. But what we are doing when we look at stability analysis locally, that we are assuming that we are moving the system in all directions, away in all of the directions. And in that case, if we move the system away in all of the directions, then this equilibrium is going to not be stable. Let's do the other one. The other one is centered on 1, 0. Okay, let me just comment my code. So that is equilibrium at 0, 0. We're going to do equilibrium at 1, 0. So the plot limit here are going to be 0.99 and 1.01, and the y limit are going to be the same. Okay. We are going to add our little dot for the equilibrium. Cool. So that is the equilibrium when the predator is absent, the prey is alone, and that's it. So what do we need to do the simulation? We need the same thing, actually. We need a very small disturbance. And then we need to add a number of random time series from that. But we need to make sure that we are starting from the correct equilibrium, which is 1 and 0. And then we can run that. And when we look at the plot in the end, what we see is it's fairly obvious what's happening. And what is happening is we are leaving this equilibrium. And if we want to check where we are ending, well, we are ending at a point that seems to be, yet again, the other equilibrium. So we've learned a second thing here, which is the equilibrium where the prey is alone is also unstable. If you have a prey that is alone and you add a predator, it's going to move to the point where you have both species in coexistence. That's for the two trivial-ish equilibriums. So let's see what happens at the equilibrium that we're going to call, at x. At what? You know what? No, I don't use I don't like the hat notation. Let's call that x star and y star, which is the equilibrium where two species are coexisting. So I'm going to do the same thing. We are going to say, so x is 0.4, so it's going to be 0.39, 4.01, and y is at 0.6, so it's going to be 0.59 and 0.61. We sort of in the middle of the plane, that makes sense. We are going to add a little bit of information by showing where the equilibrium is. Yeah, okay, it's 0.41. Okay, so that's our equilibrium. It is in the middle of the plane, and we can add some deviation around that. So what we're going to do here is, before we sort of truncated the distribution because it didn't make sense to add a disturbance that would bring the population to negative values, because that does not make biological sense. And this is a biological system that we're analyzing, and so the implementation decision that we make, this should be informed by biological constraints. And one of the most fundamental is population density is a value that is positive or 0. It's not going to be a negative value. So what that means that we can remove the truncation here. Let's get rid of the truncation. And we have our new disturbance distribution. And here we do the same thing. We make sure that we start from 0.4 plus the disturbance on x and 0.6 plus the disturbance on x. We don't need a certain time point. We probably just need 100. In fact, we probably only need 10. And let's run that. And look at PL. So that is very interesting. So we've added a very, very small perturbation, right? And there is almost nothing that has changed. Like the difference is very, very small. So let me illustrate the difference by zooming in an absurd amount on these points. So EPS here, this EPS function, is 2.22 to the minus 16. And you might recognize that as the number that R gives you when your p-value is very, very small. That is essentially 0, but not quite. And so we're going to move to that. So we are going to have a very, very, very small fraction of a plane here. And then that was maybe a little bit too much zooming. Yeah, that was definitely too much zooming. That was also too much zooming. We'll do 1 minus 5, let's say. What we should see is that it's very obvious what we should see. We should see the system get back to where it was. But I just want to show, if possible, how small the disturbance actually is. Yes, okay. So it turns out that we need a little bit more than that, probably need 100. So this is what we get, right? We start from different points, and then what we see is that these points are going to end up converging on the equilibrium again. And that's 400 simulation. Let's do 2000. Let's make them a little bit more transparent. And we can see that it's going to be, it's consistently going to get back. So we are working within the neighborhood of this point, which is a very small neighborhood, right? What we see here is it's 2/10,000 in scope on both axes. But what we see is that no matter where we start on this very, very small neighborhood around the point, it is going to get back to this equilibrium. So if we want to zoom in a little bit less, and it's actually moving from to the -5 to 1 to -4 is actually some, it's a non-insignificant amount of zoom out. But what we will see is that no matter where we start in this random position space here, we're going to get back to the equilibrium. So by way of contrast to the previous equilibrium, which was 0, 0, and 1, 0, when we moved a little bit away from these 2 points, we would converge to somewhere else. Both equilibrium were unstable. This equilibrium with both species, when we move a little bit away from it, we're going to get back to this equilibrium. We're going to get back to this equilibrium following the trajectory that we also identified when we ran all of the simulations. What that means that this equilibrium is stable. If you are near it, you are going to get back to it. It's attracting the population, the community to itself. It's something that you can't escape. That's sort of like a black hole. If you're around the black hole, you're going to go inside it. I don't know how black holes work, but anyway, this equilibrium is going to be attracting the population sizes to it. And that is something that we see by applying very, very small disturbances. So there is nothing that we have done here that would not have been achieved by a little bit of calculus. But the point was to give you an intuition for what the mathematics mean. So I'm going to assign some reading for this week, and you will find out what the Jacobian matrix is, and the characteristic polynomial, and the Routh-Hurwitz criteria, and all of these very, very fun concepts. But the important point is that you now have an example that you could use as some sort of grounding. If you say, okay, I want to check that my result makes sense. I have the predator and prey system. I know where the equilibrium are. I'm able to figure them out analytically. We've done simulation, so I can check the stability of this equilibrium through stimulation. Does it match with the answer that I get from the calculation? So that is not a difficult problem. If you want to bring it one step further, you can also try to figure out when it's going to be showing oscillation and when it's not. Or you could try changing the system slightly to see if you remove the logistic growth and the growth of the prey is exponential, do we see a different behavior? And the point is going to be you could do simulation and visualizations to help you figure out if the analysis is working as it should. So that is why I wanted to show you the simulations before moving on to the actual calculus. So just to summarize this last three modules, we have looked at way to visualize the rate of change in a system, or the first module. In the second modules, we have done explicit simulation of the behavior of the system to see that changing the parameters can change the behavior of the system, both quantitatively and qualitatively. And in this module, we have zoomed in on every equilibrium, applied very small perturbations to it, and then saw that two of them are unstable and one of them is stable. That is the non-mathematical way of characterizing the equilibrium and stability in a system. We can do all that through simulations. We're also going to learn how to do all that with mathematics. So we're going to stop this module here. What I suggest in the 10 minutes we have left is that we hop back on the Teams call, make a very quick 5-minute debrief where I'm going to assign some readings to you, and then we will continue next week.